All right, numbers seems to be quite stable, at least from what I can see. So I'm going to get this underway. So thank you all for joining us this evening. I'm going to pretend we all live in Melbourne, even though our speaker is far away from here. For those who don't know me, my name is Guillaume Roger. I'm a professor of economics at Monash University, and I work mostly on energy market these days. I'd like first, before we start proceedings, to acknowledge the First Nation people of the Curtailment Nation, on whose land we're standing at present, and acknowledge their elders past, present, and emerging, and extend a warm welcome to any of them who may be joining us today. Our speaker today is David Newbery, who is a Professor Emeritus at Cambridge. David is one of these people who need no introduction. So unlike what people mostly do, which is they introduce them at length, I'm going to say just he's very famous and we're very lucky to have him. So thank you very much, David, for addressing us all the way from the UK. It's early morning over there, but we're very happy to have you discuss your work tonight in Melbourne. Thanks very much, and please go ahead.
Thank you, Guillaume. Let me share my screen. And I trust that's now visible.
Yes, it is.
Good. Well, it's very nice to visit Melbourne virtually. The last time I came was 10 years ago when I went to the ACCC meeting and then stopped by to give a talk in the Institute of Public Administration in Melbourne. And that time it was a round the world trip. It took a long time. This is a much quicker way of making contact. But it's also an opportunity to repay my thanks. We have had Australian speakers like Paul Simshauser come to our conferences, in fact, in person, to tell us about the particular problems of high renewables penetration in South Australia. And I want to talk about the single electricity market of the island of Ireland. I have to be careful because that's Northern Ireland in the UK and the Republic of Ireland in the EU. So two quite separate jurisdictions, but a single electricity market. And they, as you will see, have to wrestle with the problem of high wind penetration in a weakly connected and small system, very similar in some ways to South Australia. So what I want to talk about is the impact that the EU demands on the clean energy packet, but also national aspirations represented in the national energy and climate plans to decarbonize and in many cases to reach net zero by 2050. And in the case of Ireland, that means basically wind. It's very well resourced for wind. And I want to ask, well, what does that massive extra wind imply for the amount of curtailment, that is wind that has to be spilled because it cannot be consumed locally? And I want to see how that depends upon the various mechanisms that might be used to try and reduce curtailment. And one of the critical constraints on a small system is the amount of inertia, and that's measured by the net non-synchronous penetration, SNSP. I'll try and explain that rather technical term later, but it essentially means that you need some spinning mass provided by conventional generation to stabilize the frequency. And if you can't do that, then you're at risk of blackouts. So just how much of this non-synchronous penetration, in other words, wind, you can absorb in the system is one of the critical determinants on when you have to curtail it. But of course, everybody thinks, well, if you've got too much, perhaps you could store it or you could export it. And I want to look into how effective those two mechanisms are and how much they can reduce the problem. So that's the basic setup. But what I discovered, and I found quite surprising, and this is what I want to share with you, is that the marginal curtailment, that is the curtailment of the last extra megawatt that you add, is very much higher than the average. And you may look at the projections for the average curtailment and be slightly alarmed at them. But if you think that marginal curtailment may be 4 times as high as that, then you can become very alarmed indeed. And that raises questions on what does this imply for the extra cost of absorbing that wind. And what I'm going to do is to approach this in 2 ways. I have a rather simple spreadsheet model which allows me to give you graphic presentations. But in order to generalize this, I've developed an algebraic model. I will be rather swift in dealing with that, but there is an associated paper that sets it out at length, and so it can be then adapted to other systems. So let's start at the beginning with the EU Clean Energy Package, and that requires all EU member states, and for our purposes, the single electricity market, the SEM, has to abide by EU laws under the withdrawal agreement. And they have to submit a national energy and climate plan, and Ireland produced one in 2020, a little bit late. And Northern Ireland has effectively the similar thing, which hasn't yet been published, but is in consultation and presumably will be delivered fairly soon. But the outlines of their plans for the next decade are fairly clear. And from that, we can infer that by about 2026, they should have 55% wind penetration. That is 55% of their electricity consumption will be met from wind. And I've chosen 2026 because by that time, the extra link to France, the Celtic link, won't be available before then, but it might be available in 2026. So we can consider how much difference that additional export capacity provides to the problem. Now, Ireland is a rather northerly and often cloudy country. It doesn't have much PV. At the moment, they haven't built much offshore wind. I think in the coming decade, they probably will. But for the most part, it's mainly onshore, but it doesn't really matter. It's mostly wind. And the important thing is that Ireland is connected to Britain, GB, and Britain in turn is quite strongly connected to France, Belgium, the Netherlands. It shortly will be to Denmark. And those countries themselves are connected to Spain and to Germany. And they've all published their own national plans. So I can work out what in 2026 those countries will be doing in terms of wind, solar and nuclear power, which again has an important property that is fairly inflexible, so it would not want to vary very much. And that's important because if that continental interconnected area has surplus wind, solar and nuclear power, then the price is going to fall to 0, or more practically speaking, Ireland won't be able to export its surplus. So we have to look at the relationship between wind in Ireland and what's happening on the continent. And at first glance, you might think, well, this looks very promising. So this is a scatter of output in the SEM, in the whole island, and what's happening in Britain at the same time. And looking at that, you might think, wonderful, they're not very correlated. So interconnection should be able to even out surplus wind in one country when there isn't surplus in the other country. But that is rather misleading, because if we work out that wind mostly blows from the west, and if you look at Britain 4 hours later, then the wind is remarkably synchronized. So when the wind blows in Ireland, 4 hours later it's blowing in Britain. And that means that if we're going to track what happens, we need a model which keeps track of time. So we need a spreadsheet that looks at it hour by hour. And that's obviously also important when we're thinking of batteries and storage, because obviously you can only fill up a battery so much. And if you run it down, then you can fill it up again. Now, the surpluses in other countries, this graph shows the wind duration curve, that is the percentage of the year that the wind will be higher than its average. So its average is 1, and you can see that for some countries like the SEM, the wind is twice its average for about 10% of the year, and that's also true in France, a bit less in the Netherlands, a bit more in the Netherlands. But if you add them all together, you can find that, again, the wind tends to be fairly synchronized. So the total wind duration curve isn't quite as extreme as the individual countries, but it still means that for 5% of the year, the wind is twice the average. And it's simple maths. If you have 50% penetration, then on average, you're going to have too much wind over the whole of the continent. So we have to keep track of that as well. And if we're going to model the system sensibly, we have to bear in mind some very important constraints on how electricity system works. Clearly, you don't want blackouts. You want the frequency to be stabilized. If it goes outside a very narrow band, then plant is disconnected and you get rolling or cumulative blackouts. And in the case of the SEM, which has a peak demand of about 4,500–5,000 megawatts, they have to have at least 5 units running if the system is to remain stable. And if you run them at their lowest stable level, that accounts for 795 megawatts, which is quite a large fraction of the total demand. You also have to make sure that if you lose a single large generator or a single link from abroad, then you have to be able to immediately replace it, again, to avoid a blackout. But that turns out to be less important than the stability requirement. And then we come on to the simultaneous non-synchronous penetration, which is a lengthy way of describing wind and PV in particular, but also interconnectors, which are not synchronized, which are not, don't have spinning mass or inertia, so that if you suddenly lose power, the mass continues to spin and continues to provide power for some time. And that means that you need 25% at least of this spinning mass to make sure that the system has enough inertia to retain its stability. Or putting it another way, the non-synchronous generation, the wind and the PV, but in Ireland mainly wind, has to be less than 75%. That's the 2020 target. And in order to do that, then you have to make the system more resilient to variations in frequency. And that's measured again by one of these technical terms, the rate of change of frequency, the rock-off that the system can allow. And at the moment, the system in the SEM is being adapted to raise this to from 0.5 hertz per second to 1 hertz per second. And this is very challenging. Britain, and I don't know what's the case in Australia, but 1/4 hertz per second is quite common. And that means if you want to retain your frequency within a band of 49 to 51 hertz, in Britain, you have 4 seconds before you hit those boundaries. But if Ireland raises its rock-off to 1 hertz, you've only got 1 second before you're running into trouble. So you need to be able to respond quite quickly. But that does mean that you can accommodate more wind on the system. And the ambitious target is to raise this to 85%. That's going to require a lot of adaptation of all the equipment on the system. It hasn't yet been achieved. We hope it will, but I'm going to consider that that has been successfully done. Well, if you reach all these limits, then you have surplus wind, and you then ask, what can you do with it? And you can't export it if the neighboring countries have already reached their limit, but you can store it if you have some spare capacity. And there's a pumped storage plant in the island, which can take 292 megawatts for 8 hours. And there's battery electric storage, and by 2026, they expect to have 500 megawatts, but you can only fill it up for an hour. And possibly by 2026, there will be a large number of electric vehicles. And if you could control when they were charged up, and if there were some of them that were not yet charged up, you might be able to put in an extra gigawatt hour of battery storage. But that would require a lot of adaptation of the system, so that's something to come. And again, if you're looking for demand side response, perhaps with immersion heaters heating up hot water, if you can control them, and if they hadn't yet heated up the water, you could use that as an extra demand to absorb the surplus wind. So there are possibilities, and the question is, how significant are they and how much can they reduce the problem? The problem being, we really don't want to waste the wind that we've expensively installed. So this gives you a graphic picture of why you need to worry about the system non-synchronous penetration or the wind penetration. And you can see the blue line there, red on the right-hand axis, gives the percentage of wind essentially on the system. And the green is the gas, which is basically all of the rest of the fossil generation. And when wind goes up, gas goes down, but it can only go down a certain amount. And you can see already the peak is over 65%, and they want now to raise it to 75%. But the planned increase in wind is also quite considerable, which we shall now look at. So the SEM has been expanding its wind capacity and will continue to do so. And I've taken, you can see that the capacity factor, how much wind you get per megawatt of wind capacity, varies quite a lot from year to year. But looking at the average over a run of years, it looks like 2018 was an average year. And so in order to work out how much wind I will have in 2026, I scale up 2018 by a factor of 2.18. You can see this is quite an ambitious rate of expansion, but it's one that is considered achievable. And from that, we can work out what 55% penetration would be and how much we need to expand capacity. If we again look at these duration curves, which is a way of ranking the fraction of the year that the output or the demand is higher than a certain amount, in this case megawatts, you can see that wind in 2026 would appear to considerably exceed demand for a small number of hours of the year. And the demand itself peaks, but is then obviously the off-peak is only about less than half of the peak. And if you add on exports, it slightly increases the potential demand that you could use to absorb the wind. But of course, these have each been ranked separately. So I'm looking at the peak wind, but that may not, and in fact, typically does not coincide with peak demand. So we have to look at what's happening at the same hour of the year. And I'll come on to that in the modeling. So if I were to step you through the sequence of questions I ask, I have some surplus wind, can I export it? And that means checking whether my neighboring countries are in surplus or not. And if I can't export it, then I ask, have I reached the SNSP limit of 85%? And if I have, then I've still got some left over, then I can put it into storage, at least until the storage is filled. and anything beyond that has to be curtailed. If, on the other hand, I can export, then I can produce 85% locally wind of the demand plus the exports, that's all demand, and export that, and then the surplus can be put into storage. And I'm going to then work out how much curtailment I have, and then redo the calculation with 100 megawatts of more wind and see how much extra curtailment I have. And that's just a simple algebraic calculation. So to give you some examples, if I have 75% SNSP, which is the current standard, 75% wind on the system, then you can see that 30% of the time I have more winds than would meet that limit. But if I was allowed up to 85%, then that would drop to 25%. And the area under these graphs will be the total amount of wind that is going to be curtailed. And you can relate that to the amount of wind on the system on average. And you can see that these curves are higher than the ones that you might think just by looking at the wind less demand curve, or the wind after I've exported surplus, which would suggest that you have, if you were exporting and if you were injecting into storage, less than 10% of the wind would seem to be curtailed. But the problem is that the demand and the wind don't occur at exactly the same time. And that's the reason why the amount that you spill is larger. If you have a lot of wind in the middle of the night, then you're almost certainly going to have surplus. So let's now look. Behind this is a spreadsheet. I go through the steps for each hour of the year in 2026, and I work out, first of all, what effect changing the system non-synchronous penetration, the share of wind, has. And at the present standard, or the 2020 objective standard of 75%, 13.3% of the wind that potentially could have been generated will be wasted. But if I step that up to 80%, then that drops to 10.4%, and 85% down to 8.1%. So for each 5% increase in that penetration, I'm initially saving 746 gigawatt hours of energy that otherwise would be wasted. But the amount decreases as the penetration that I'm allowed goes up. And I might worry a bit about whether taking an average year is on average the same as a mixture of windy years and calm years. And you can see that it's the average spill is slightly higher than the spill on an average year. So the windy year, you get much more curtailment than you avoid in the calm year. But the difference is not too enormous, so I'm not going to worry too much about simulating a number of years. That would be something for a proper consulting effort to undertake. And what about increasing battery electric storage? So if I start off with 500 megawatts, that's what's planned at the moment, and there's every reason to expect they'll have that. If I have that, then my curtailment is 2,000 gigawatt hours a year. But if I add an extra 100 megawatts, then I only save 18.5 gigawatt hours, which is not a lot. In other words, batteries actually don't help reducing wind storage very much. And you can see that what that is, the amount that I've saved is less than 3% of the storage capacity. So it's a very expensive way of solving surplus wind. And you can see the effect again of halving the storage capacity. It doesn't have a large effect, or doubling it wouldn't either. So storage is less promising than one might think. How about extra interconnection? Well, at the moment, Ireland has about 900 megawatts of link to Britain, and that's 900 compared to a peak demand of about 5,000 megawatts. So it's quite a large fraction. And 700 megawatts of extra link to France would seem to be quite a big increase. But surprisingly, it only saves you at 85% SNSP, it only saves you 275 gigawatt hours. It doesn't have a huge impact. And even the 900 current interconnection only saves 900 gigawatt hours. Again, it doesn't have a huge impact on the amount of curtailment. So these apparently attractive alternative ways of dealing with surplus wind are more limited than one might expect in a small system like Ireland. Again, obviously, if you're sitting in Germany surrounded by a large number of other countries, your options are much stronger. Now, I said that I've done this all on a simple spreadsheet, and you can download it if you want to from the EPRG website. But the algebraic model works on the principle that the curtailment schedules that I showed look pretty linear. And more to the point, they move in a fairly linear way. This shows the effect of adding an extra 1,000 megawatts or subtracting 1,000 megawatts of wind in 2026. And those schedules move in a fairly parallel way. And the linear approximation turns out to be quite good at reproducing the results of the complicated spreadsheet that takes all these things into account. And I'm not going to dwell on the mathematics, but they do allow me to calculate what the marginal curtailment is. And that is surprisingly high. So these parameters, the alpha and the A, are the slope of the curtailment curve and the intercept of the curtailment curve. So those are fairly easily read off. And the answer comes to be a surprisingly large 4-to-1. And that matches up with the detailed simulation I've got. So I have some confidence in the algebraic model. Well, then we can ask, well, all right, how does this influence the way in which you think of installing extra wind capacity? If a large fraction of it is going to be wasted, does that affect the cost of meeting the targets? So we can work out what the social value of adding a megawatt of wind is, and what it allows you to do is to reduce the amount of fossil generation on the system. I'm supposing the demand doesn't change, so the main impact is reducing fossil generation, and that saves you some cost of capacity and also some running costs. And the running costs there depend on how much wind is, how much generation is displaced. So the term in brackets, this term is the annual fixed cost of the wind, and the variable running costs, which may be fairly low but aren't zero, depend on the fraction of the time that it's running during the hours. This is the full hours of the year, and these are the curtailed hours. So this is the hours that it actually runs. And so the social benefit is the saving in the cost from the fossil plant minus the cost of having to install the wind. But that's the social value. And we can now ask, well, does the market give the right signals? What is the market surplus? What is the profit that a generator would get? And that's actually quite different because the social value depends upon the marginal curtailment, but the market value depends on the average curtailment. And the difference between the two is the extra cost. I'm going to argue that it is a cost that wind imposes, that the extra wind imposes on the system. And it's made up, this corrective charge, when you do the algebraic modeling, of 3 terms. Now this term, delta W, is the capacity derating factor for wind. So if you look when the system operator is working out what the contribution of wind is to system reliability, he comes up with a number. And in the case of Ireland, he says, well, although the average wind output is about 28%, in stress periods, we're going to only assume that 10% is available. Because we're going to be cautious and we're worried about years in which the wind is much lower than average. And the capacity factor on average in these hours of stress, the highest demand, less wind hours, will typically be considerably higher, because we're looking here at the average, whereas the system operator is very cautious and is worried about worst cases. So the market is going to over-reward wind, essentially because it doesn't penalize them for not being there when things are really bad. And wind in that way is quite different from ordinary generation, because when the system operator is worried about the system reliability, he can reasonably assume that if one generator fails, the others won't at the same time. They're independent events, they're accidents. But if the wind isn't blowing, it's typically not blowing for everybody. So a single wind farm is really like a very, very large single generator. And as such, it's much riskier. And that's why it's derated more heavily. But on average, it's actually going to earn quite a lot of money. And so it's being overcompensated. This term is just a very small amount of saving in costs that running the wind and displacing fossil generation provides. But the last term is the marginal curtailment factor. H is star is the number of hours that the wind operates, and that will change when the capacity W of wind increases. So we could say, well, let's concentrate on the marginal curtailment effect and assume that the market, that the derating factor is adjusted so that wind on average doesn't make profits out of being available some of the time when there is a scarcity. And that's an assumption. Now, offsetting that, we know that as you increase the amount of wind that's built around the world, the costs come down and have been coming down very steadily for a long time. And this learning externality, the spillover, means that when I order another wind farm, the manufacturers and the developers and the inventors all get to work and think of better and cheaper ways of doing it. And those benefit subsequent installers of wind farms, because I have ordered one, I've created the demand that's helped drive the cost down. And if I work out what that external benefit to the rest of the world is, I can say that on average in 2026, it looks as though it will be about 10% of the fixed cost, with quite a wide range. And the marginal curtailment factor, this corrective charge, is about 20% in the pessimistic scenario in which I cannot increase the penetration of wind and I don't have any extra links to the continent. But if I am more ambitious and do have the link and increase storage, then that curtailment drops to 10%. And you can see that lies within this range. So you could say that although wind imposes a cost on the local system, it creates a global benefit. And in a world in which we're trying to reach international cooperation on climate change, that should be recognized. So perhaps we shouldn't worry too much about that. So what does this imply for policy options? Well, you could, if you were a very pro-market person, say, okay, we'll subsidize wind for its learning and impose a corrective entry charge, and then let things work to the social optimum. Or you could just say they're about the same, so we'll ignore both. Or, and in practical terms, this is what most countries do. You say, if we've got a target, we're going to auction so that we reach this target, and we'll work out what capacity subsidy is needed to reach the target. And if you do that, you should be very careful that you don't distort the market. And the simplest way of doing that is just paying for the first 25,000 or whatever full operating hours, so that it's a subsidy to capacity and not to output. And then it won't distort the dispatch and pricing in the market. So, to conclude, the surprising and I think important result in isolated systems, and I come back to South Australia, is that once you get to fairly high levels of penetration, then the marginal curtailment can be much higher than the average, and the average can be quite high itself. And this can be ameliorated, but not as much as one might hope. And the consequence of that is that you're getting less money than you might expect from the extra wind. And so you're over-rewarding wind capacity through the capacity mechanism if you have one. And the bottom line is that the social value is determined by its marginal curtailment, but the market revenue is dependent upon the average curtailment. And that's, if you like, the market failure that needs addressing. And it's offset by the learning externality. So the implication is probably the market is an unreliable mechanism, and auctions seem to be a more effective way of delivering targets. So I will leave it there. And shall I stop sharing my screen?
Thank you, David. Are there any questions in the audience? No one seems to be willing to take the first step. So I will ask a question. Maybe it's a silly question, but would you be able to explain the mechanics whereby batteries are so ineffective at absorbing this extra energy? So why is it that they essentially don't have very much in wind curtailment?
Yes, that's a very good question, and it has a number of dimensions. The very short answer is that batteries, lithium-ion batteries, which are probably the preferred form, have an ability to absorb quite a lot, but for a relatively short period of time, somewhere between half an hour and 2 hours. So it unfortunately doesn't take long to fill them up. And they're very expensive. So buying a 100 megawatt battery, which is what South Australia did, was pretty pricey. And in practical terms, what those batteries are mostly useful for is very short-term flexibility response. So they're very good at providing stability to the system. If you are using them as they're often used for solar PV, it means you can even out the rate at which you deliver to the grid. You can avoid constraints on the system for short periods of time. You can do peak lopping. You can shift demand sideways by an hour or so, and that can be very valuable. But the wind tends to blow for lengthy periods, and it doesn't take long to fill up the battery. And that, in a nutshell, is the limitation. And the economics, if you look at how the business case stacks up, typically only about a quarter of their revenue comes from arbitrage, buying when the price is zero and selling it later. That's dealing with the surplus wind. Most of it comes from ancillary services.
Yeah, absolutely. That's very much the case in South Australia. Other questions from the audience? Okay, so Then I do have another question, which is, it's not really the same question, but as to why adding this transmission link to France, for example, would also not help very much. Is it because now wind is synchronized between Ireland and France, for example?
Yes, that's exactly the problem. And the great concern in Europe is if you have a cold and therefore high heating load period in the winter with still wind conditions, those still wind conditions can spread over the whole continent. So you do get some benefit from, as I say, the time difference. It does take a few hours for the wind to pass from the east to the west. And on the continent, that's quite valuable because they're strongly interconnected. But between Ireland and Britain, it's much less valuable.
I see. So there's a question from somebody. I'm going to try to read that. It's in the chat box.
Is the market failure to do with the capacity payment?
That's the question from David Scott. Yeah, thank you.
So there are actually several market failures. The one I like to think of, the wind curtailment one, is a tragedy of the commons. So you can think of it this way. When you've got fossil generation on the system setting the price, that's of value to all of the wind farms. But the moment you have too much wind, the price then should drop to zero, or its marginal value drops to zero. And the last person in drops the value for everybody else. So if you like, the fossil generation is like the commons, and if all of the cows are allowed to roam on it, adding an extra cow harms all the other cows, and that is the source of the public good market failure. The capacity failure is a problem of how you reward reliability, or put another way, how you penalize the lack of reliability. So an individual fossil generator, as I say, it has maybe a 5% chance of failing in some period, which is quite independent of all of the other generators. And so you can think of just losing one generator, and in a big system with maybe 200 units on it, that's a very small risk. But if half of your energy is coming from a single generator and you lose that, then the damage done is not a marginal damage, it's much larger. And so it's the difference between the average and the marginal damage. And I think people have been wrestling with how do you work out the value, the contribution to reliability of intermittent generation, PV and wind. And the answer is quite sensitive to how much you have on the system. If you don't have much, then you can take the average reliability because it's like a small generator. But if you have a lot on the system, and that's the direction we're moving, then you can't any longer treat it as a small isolated event. And therefore, the risk it imposes on the system is much larger than it might appear. And that's, if you like, a market failure. If you inappropriately pay for its availability during stress periods, you probably over-reward it.
Sorry. So there were a couple of questions from David Prince. Question number one is there any need to retain some fossil fuel rather than go to zero carbon? So should we retain some of the thermal generators for the purpose of, say, reliability or inertia or things like that?
So to take the inertia, there are other ways that you could provide it. I mean, people have suggested flywheels. It may be that sophisticated power electronics can provide synthetic inertia, and this is a very active field of research. But the simplest is just to have spinning mass provided by generation. Looking at the 2050 scenarios, they're now concerned with, well, perhaps you could provide it by conventional generators running on renewable fuel, whether that's hydrogen or bioenergy with carbon capture and storage or something like that. But the inertia on the system, if you want to stabilize frequency, you need some form of inertia or synthetic inertia. And the simplest way of having that is to keep the old plant where it's going to be, providing it can be activated fairly rapidly as the potential spinning reserve. That's satisfactory until you get down to very low levels of carbon. And then you have to think of non-carbon synchronous generation. And in Europe, the most obvious one is nuclear power.
Thank you. Follow-up question from the same person, from David. I'm going to abridge it because I think you answered that in part already. So if we keep those conventional generators online for the purpose of system reliability, for example, how will they be paid enough to be economically viable if they don't generate that much energy in the end? So I presume this is asking, you know, what other forms of payments do we need if they really cannot be paid for the energy they produce?
Yes, well, we, Britain, had an energy market reform in 2013 precisely to address this question. And the answer was, you have a capacity auction and you ask them, how much do you need to be paid to stay on the system and to be available when we need you? And you can do the sums and calculate how much money you'll make from all of the other things you do, like providing ancillary services or selling energy. And the shortfall, you can tell us how much you need. And in a competitive market, we'll then find the cheapest solution to that. Mm-hmm. And I know there's a huge resistance in many countries or to capacity payments and the idea that you should just have an energy-only market. It always struck me as very strange that when electricity provides three things at least, one of them is capacity, one of them is energy, and the final one is the quality of service, the frequency stability and the voltage stability, that you would only ever pay for one of those. But it's an argument that is strengthened in countries that have so much surplus generation that they get the other factors for free. And the moment they start running out, then they realize that these need to be paid for as well.
Well, I can report that those conversations are occurring in Australia almost as we speak. So,
well, you can either do it ex post by saying, if there is a shortage, we'll pay you an arm and a leg for having been there, or you can say, we'll pay you up front for making sure that you really are there. One just needs to compare and see which system produces the best result for the least cost.
Excellent. I think there's another question in the chat. Can you see, David?
Why do consumers need to throw away reductions in costs anyway? Won't investors take account of that? So better to let them do it. Well, if you had a single monopoly supplier of wind turbines, as you have a single supplier of some patented drug, then obviously they would take into account all of the future profits that they would make from expanding their capacity and doing the research and development. But that's not the world we live in. If I invent a better wind turbine, it will probably be manufactured in China and sold to me at a lower cost. So I don't get the benefits of my research and development. I can patent it, but that's only a small part of the learning benefits, the know-how, the economies of scale, the assurance of a future market. All of those things are the sorts of things that investors need in order to bring the costs down.
All right, then we seem to have exhausted the questions and exhausted the audience. So
it is a technical paper, which is why I've I imagine you can post the version which has the references at the end, and those who are really anxious to fully understand it can penetrate the algebra at greater length. But I appreciate that it is a mixture of the technicalities of an electricity market combined with the technicalities of dealing with a particular market failure, and as such, it's a tough sell.
No, I think it was very interesting. I don't take it as a tough sell at all. Electricity markets have always been complicated. They're only becoming more complicated because we have this generation mix that's coming in now and making our life a little bit easier, a little bit harder. But we'll definitely post the paper. We'll post also the recording of this session so people can go back and listen to David's explanations again if they wish. I want to thank you very much again for addressing us today. In normal circumstances, we take you for a drink or something nice. Unfortunately, we cannot do that today, but I would like, fantastic. I'd like to ask the audience for a virtual clap, and thank you again very much, David, for talking to us today.
It's good to meet you all, but if only virtually.
Well, thank you very much, and I'll see you soon, I hope, on either in Britain or here in Australia. Thank you.